And now part 3 of our video lecture series, Transport of Oxygen and Carbon Dioxide. In the previous lectures, we focused primarily on the immediately previous lecture, we focused primarily on how do we load and unload oxygen and carbon dioxide from the blood, or how does it follow those partial pressure gradients. Now we're going to examine exactly how oxygen and carbon dioxide are transported within the blood. First, looking at oxygen transport. Remember, oxygen has very low solubility in water, so very little of it will be dissolved directly in the plasma. Only about 1.5% will travel dissolved in the plasma. So we have to have some alternate mechanism to transport the oxygen, and that's bound to a molecule called hemoglobin. Hemoglobin is a very common molecule. It's actually found in all the kingdoms of life. In vertebrates, hemoglobin is made out of 4 polypeptides, each of which has a heme portion with an iron. So 98.5% of the oxygen circulating in the human body transports in the hemoglobin in the red blood cells. The only portion of the hemoglobin that can bind oxygen is the heme portion. Each heme portion contains an iron, so we have 4 globins, 4 hemes, and 4 irons, so each hemoglobin molecule can transport up to 4 oxygen molecules. We call the form of hemoglobin when it has oxygen attached oxyhemoglobin. So oxyhemoglobin is hemoglobin with the oxygen attached. Now, here's the problem. Only the dissolved portion of the oxygen can diffuse into and out of the cells. So oxygen has to be able to bind to the heme portion, the hemoglobin, and dissociate or break apart from the heme portion. All right, so this scheme should look a little bit similar to what we've seen before, but now we're focusing in on the transport of the oxygen and also the transport of the carbon dioxide. So if we look coming out of the alveoli and down into the blood, we see that only 1.5% will be dissolved, only about 1.5% will be dissolved directly within the blood plasma, whereas 98.5% will get attached to the hemoglobin in the red blood cells. All right, so it transports then to the heart again, to the left atrium, to the left ventricle, and out to the aorta, and from there out to the tissue cells. All right, only the dissolved portion, the oxygen, that 1.5% that is dissolved, can make its way out to the tissue cells. So that means we have to have some mechanism to take it on and off of that hemoglobin. All right, so how do we do that? Or why does it bind to hemoglobin so easily, and then also has the ability to unbind from hemoglobin so easily? Well, there's a relationship between hemoglobin and the partial pressure of oxygen. The higher the partial pressure of oxygen, the more the hemoglobin will bind with the oxygen. The more oxygen combines with hemoglobin. In fact, under a high partial pressure of oxygen, the hemoglobin molecule is literally changed, where it will very securely bind the oxygen. All right, so fully saturated blood, if blood was 100% saturated, then every single one of the hemoglobins would have 4 oxygens. It would be fully converted to oxyhemoglobin. The percent saturation of blood represents the average saturation of hemoglobin with oxygen in all of those red blood cells. So, for example, if you took a person's O2 saturation, you might typically see anywhere from 97 to 99% saturation. You're very rarely going to see an individual who has 100% oxygen saturation. And often the lower this is, I wonder if you guys saw that it is now expected to be precipitation later on today. Let me close that out. Sorry. The lower it is, that indicates some problem with loading the oxygen onto the hemoglobin. All right, so we're going to next look at something called an oxygen hemoglobin dissociation curve. And there's a lot of information we can get from the graph that I'm about to show you. One of the main things I'm going to point out is two distinct regions of this graph. One portion of the graph is typically what we see in pulmonary capillaries. This is going to be around the alveoli. The partial pressure of oxygen will be very high, and we see that hemoglobin under that high partial pressure really loves oxygen and it binds tightly. But then we're going to move to the tissues in internal respiration, and we'll see that around the tissues there's a much lower partial pressure of oxygen, which means that the hemoglobin will change and it doesn't hold the oxygen as well, so it will unload the oxygen. Right? But still, in an average tissue, resting tissues, there may still be 75% remaining in that reserve. So 75% still in that deoxygenated blood. So let's have a look at the oxygen hemoglobin dissociation curve. And remember, I said we were going to look at two different areas of this graph. All right, so let me just draw a line right down, a wiggly line right down the middle of this graph. All right, so the area up here is typically the area that we see in external respiration. So this is what we typically see in external respiration. This is going to be around the alveoli, where you have a very high partial pressure of oxygen. So down here, we see the partial pressure of oxygen is on the x-axis. That's written in millimeters. And remember, about the highest partial pressure of oxygen that you can see, is going to be around 100 millimeters. Then over on the y-axis of this graph, we have the percent saturation of hemoglobin. On average, how many of those hemoglobins have oxygen attached? Is it 100% of them have it attached? We would say 100% saturation. Are only 50% of the hemoglobins fully full of oxygen? We would say we were at 50% saturation. So up here at our very high partial pressure of oxygen, we see the highest amount of saturation. All right, so we have our highest level. If we go over here, we can see that we are nearly at 100% saturation. All right, nearly at 100% saturation. So that's what we see around the lungs. Now we're going to take that oxygenated blood, those systemic arteries, move it through the heart, out to the systemic arteries, and move it to the capillary beds at the tissues that will need some oxygen. So now we see the rest of this graph, this other side, is the side that's associated with internal respiration. So this side is more internal respiration. Okay, so let's look at 40. So let's say we have a partial pressure of oxygen of 40 millimeters of mercury. That's a very typical average cell, right, at rest. And if we look, we can go up and see where it contacts. Right here, it's going to contact right here, that line. Okay, and if we follow over to our percent saturation, we can see that that area will probably drop the percent saturation down to around 75%. All right, so we have a 75% saturation at 40 millimeters of mercury for the partial pressure of oxygen. So that means that this, if I go up here, capture this top level of the graph, all the way down to capture about where that is the amount offloaded onto those average resting. And that's going to be about 25% of the available oxygen. Now, let's say that you had some tissues that were very metabolically active. You're running, and your large skeletal muscles are using up lots of oxygen because they have to create lots of ATP. Well, you may see the area around those drop down all the way to maybe 20 millimeters of mercury for oxygen. So once again, let's look at our graph. We'll follow the dotted line up, and we'll see where it intersects and go over, and you can see that there's even more oxygen that's available to be offloaded. All right, so now if we look at that tissue, so we would be up here for our original, all right, and go all the way down to about here, and that's the amount that would be offloaded. It's not 100%, it's probably about 60% offloaded. All right. But the point is, you are delivering a lot more oxygen to those very active tissues. So the more the tissues need the oxygen, the more oxygen that's available, because the partial pressure of oxygen is literally changing the shape of the hemoglobin slightly to make it more or less able to bind the oxygen. If you have a high partial pressure, it changes the shape of the hemoglobin and makes the hemoglobin really bind the oxygen. If you have a lower partial pressure environment, then the hemoglobin is changed a little bit again, but it makes it so it doesn't hold the oxygen very well. So you can deliver oxygen to the tissues. Okay, so that's one way you could look at this oxygen dissociation curve, is looking at the difference between external respiration and internal respiration. But let me show you a different way that we could look at this. I'm going to erase a bunch of this drawing that I've put on here. And think about this in terms of disease. Okay, so we're mainly going to focus on the top part of this graph. All right. Okay. So, if you have healthy lung tissue, all right, healthy lung, then all the factors that will allow you to load in oxygen very quickly are going to be there. You're going to have a lot of surface area of lung. There's no damaged area to the lung. The diffusion distance is very small because you don't have any scar tissue. So in a healthy lung, you expect to see the ability to load in a lot of oxygen. But in a diseased lung, where you don't have that, you may see a much lower area, an area where you cannot load in as much oxygen. So someone who is in a disease state, no matter how hard they try, cannot carry as much oxygen. That was supposed to be a straight line, y'all. And if they get even in a poor disease state, then maybe they could only get in the 80s for their saturation, right? So they may see very low oxygen saturation. Well, look at this difference right here. If this is the amount of saturation they can get coming out of their, that would be in a diseased lung, coming out in their diseased lung, and here's the average that gets offloaded at the resting tissues, that's not a lot of oxygen, right? That's just not a whole lot of oxygen. So what could you do to increase the amount of oxygen that got loaded into this diseased lung? I'll give you a second. You could have supplemental oxygen. Supplement with oxygen. So someone would have to wear a nasal cannula. Usually you'll see these people who have diseased lungs walking around with a nasal cannula, taking in some supplied oxygen, some pure O2. What is that going to do? What is this supplemental oxygen going to do? It's going to raise the partial pressure of oxygen in the lungs. All right, down in the alveoli. If you're breathing in 100% O2, then that partial pressure of oxygen is going to go way up. So that will hopefully be enough to overcome the damage to the lungs to raise that percent saturation back up to what you would see in a healthy lung. All right, but there are other factors that can affect the love of. The affinity means love of or like of. The affinity of hemoglobin for oxygen, which is really just how well does the hemoglobin bind the oxygen. And each of these will make a little bit of sense if you keep in mind what's happening in a metabolically active tissue. They need oxygen, yes, but if they don't have a lot of oxygen, they're probably going to use anaerobic cellular respiration. Anaerobic cellular respiration will produce lactic acid as a byproduct. So you will change the pH. It will become increasingly acidic around the metabolically active tissue. The partial pressure of carbon dioxide around that tissue will also go up. As it's consuming oxygen, it will be producing carbon dioxide. And the tissue may heat up. When you use your large skeletal muscles, you're going to be producing some heat as a byproduct. So we could have a change to pH, the acidity could change. You could see a change to the partial pressure of carbon dioxide as you start producing more. And the skeletal muscle, for example, may heat up. You'll see a change in the temperature. So let's see what these do to the oxygen dissociation curve. So up at the top, the top graph you're seeing is the effect of a change in pH on this oxygen dissociation curve. So the middle one, the black line, is the normal blood pH. Blood's pH is typically going to be 7.35 to 7.45. All right. So if you're sending blood through some of these large skeletal muscles that are actively using anaerobic respiration because they don't have enough oxygen, they're going to be producing lactic acid, you expect for the pH around those tissues to go down. So if you look at that graph again, the red line, so the black line is normal. There's the black line is normal. The red line shows low blood pH. And let's see what has happened to the affinity, the love of hemoglobin for oxygen. So first let's look at, well, so 30 would be the need in a moderately active tissue. So that's why this line is placed here at 30. So we see what this would be in a normally active tissue. Okay, so we go up, and first let's see where this intersects the black line right here. All right, so we'll see where it intersects that black line. And if we go over from there, all right, go over from there, yeah, that's about right, we can see that the percent saturation at a partial pressure of oxygen of 30 is about probably 50% saturation. All right, but if we lower the pH just a little bit, so we lower the pH in that area, so we see here a little bit lowered pH, and now we go over, bump, without the little tail at the end, we can see that the percent saturation is even lower. That means that you've delivered even more oxygen. So it would have gone from this normal level of close to 100% saturation. If we didn't change the pH, that would be the amount that would be released, but because the pH has an effect on the hemoglobin, we can add in a little more oxygen released. All right? So this is great. When your cells are very metabolically active and the pH is a little lower because it's been having to rely on anaerobic cellular respiration, you can physically deliver even more oxygen to the tissues because the acidity will change the hemoglobin slightly as well. Now let's look at the effect of a change in the partial pressure of carbon dioxide. All right. So if your tissues are very metabolically active again, so once again we're going to look at tissue range of about 30, a moderately active cell. It's using up a lot of oxygen and it's also producing some carbon dioxide. So in this area that's producing some extra carbon dioxide, if we look, here's where it intersects the line for normal, here's where it intersects the line for extra carbon dioxide, and once again you can see that if we go from where we first saturated the blood all the way down to the first level, that's that amount of oxygen that's released, but we get a little bit extra because a high blood carbon dioxide level will allow more oxygen to unload from the hemoglobin. Right, now let's look at this graph from the other direction. Let's say that you are, well, anyway, trying to see where I can show you this. Let's say that you are up at the lungs, and at the lungs right here you've just offloaded a bunch of carbon dioxide from the lungs, and now you want that hemoglobin at the lungs to pick up as much oxygen as possible. So you can see that getting rid of the carbon dioxide at the lungs allows you to actually load in a little more oxygen onto the hemoglobin than you would normally have predicted. And then we also have the temperature changes. And this is going to be within limits because limits that will sustain life. So we're, a lot of times when we think of the normal blood temperature, we think of our normal core body temperature. But sometimes, and we would normally think if you saw a body temperature of 110 degrees Fahrenheit, that person's not long for the world. But that's your average blood temperature. This is the temperature that you might expect to see in an actively working skeletal muscle cell. Right? It's going to be very different than the temperature of the blood by the time it makes its way to your brain. Okay, so we could see temperatures in very active, metabolically active skeletal muscle locally getting up towards 43 degrees Celsius or 110 degrees Fahrenheit. All right, so what happens when we get that? Once again, we see, let's say we have a moderately metabolically active tissue, like here at around 30 degrees, 30 for the partial pressure, moderately active. In a normal tissue, here, right here, is where you would see the intersect, right? That's going to be nearly, whoops, if I can draw a straight line, nearly 50% saturation. But if we look at the line intersect for really hot tissue, right here, you can see that it's much lower. So there's a greater amount of oxygen that can be released. Okay. Here's a little problem though. We see the exact opposite occurring with hypothermia. So in hypothermia, you see this really strong tendency of hemoglobin. You see this really strong tendency in the blue line for hemoglobin to bind oxygen, and it's not going to release it that well. So that's one of the dangers associated with being hypothermic, is that the blood will hold oxygen very well. But in a way, it's also one of the benefits, because if you do quit breathing and the body is hypothermic, you do retain a little more oxygen in the blood for a longer time period. This could keep a person alive a little bit longer if they were no longer breathing at a cold temperature versus in a warm temperature. So, for example, a drowning victim. A drowning victim is much more likely to be resuscitated if the drowning victim is in a frozen lake compared to, I don't know, the middle of the Gulf of Mexico in summer. Okay, so temperature changes. So we've looked at 3 different ways that we could change this oxygen saturation curve. The pH of the blood, the partial pressure of carbon dioxide, and the temperature of the blood. All right, and then there's another way. The difference between fetal blood and maternal hemoglobin. So fetal hemoglobin has a really high affinity for oxygen. And remember, a fetus is getting oxygen from mom, not from its own lungs. Fetal hemoglobin can carry 30% more oxygen. So this means that the maternal blood doesn't hold the oxygen as well as the fetal blood, so it's really easily transferred over to the fetus. All right, and I'm going to pause here, and on our next video we will take up carbon dioxide transport and probably finish this up. So that's the end of part 3. You should look next for part 4.